All right, good morning. Today is July 24, 2024. So 24/7/24 or 24/7/7/24, something like that. No. Okay, July 24th, 2024. All right, so one thing here is I put a little bit of labs notes. If you noticed, all the lab submissions are open for by now, except for that one coaxial cable lab. That's because I need to give you a little bit more information on this one before I open that, so you can properly submit the deliverables. All right, everything so far is well. The labs are pretty much it. 12 labs, not gonna have any more than 12 labs. That should be enough. So from now till the end of the class of the school term, we just need to complete all the labs. So just keep showing up as per schedule for this week, and then from then on it's going to be open sessions. Okay, just so we can tie all those loose ends, so everybody's going to have. We have done a lot more labs than the class last year, and it's simply because we're going back to the pre-COVID thing that took us some time. Yeah. All right. So first things first, when it comes to oh, there's one more thing. I'm going to release a test later on this week, and I'm going to give you enough time to complete. That's going to be test 3, and at the end is going to be test 4. Test 4 is going to include pretty much most of the questions from the whole term. So that should be no problem, since still the rules of the tests for my class here are same as for well, the test 4 is going to be under the same rules that all the other 3 tests, including this one that's coming up this week. All right. Now let's take a look at something here. Content. Actually, first of all, let me make myself look like a student. All right. Content, labs, and see here, blank lab work orders. And this is for the coaxial cable. So this group that was on Tuesday got the other regular work order, and we should have distributed that one. So that's a little bit on my part. There are 1, 2, 3, 4, 5 questions to be answered. So since the group from Tuesday got the other work order, I'm just going to ask you to do a little extra thing for me. All right. I do a lot of extra things for you. Do one thing for me. Can somebody do one thing for me? No, just kidding. Copy those questions and put the answers, because in the rubric there, and I just want to point that out to you. So just copy those questions by hand, right, and write the answers beside it. 5 questions. We need to see 5 questions, 5 answers. Because here, if we look at the submissions, yeah, well, in this case, I need to go and make myself look like myself. So if I go to the rubrics, and let's take a look, coaxial cable rubric. There you go, lab 11. Da 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 da. See here, that criteria, questions answered, 5 correct answers, 10 points. So that thing is worth 10 points. So we need to do that. And the class that is going to be the rest of the class this week, and if you ever do that coaxial cable, we just need to grab those, and I'm going to print some extra copies. We need to grab those other work orders just for that coaxial cable lab. And if you by mistake grab the other sheet, just copy those questions right, by hand and give the answers. Now, I need to give you some information so you can answer those questions correctly. There we go. Here is our class. Let's see here. Here's something to think about. And let me just zoom in a little bit. Here's a multimeter, and let me double click on that. This is multi-sim that I'm using here. I'm bringing the display of an ohm meter here. All right. Now I'm going to need your participation on this one here. So pipe in on voice if you want, or type on chat, in chat window here. Let me connect this thing here. Open the switch, and I'm going to connect right through the switch, and here. All right, so forget the reading right now because simulation is not on. Okay, so I'm going to get that thing out the window here. Now this resistor is not in the picture, so it's not connected in the system. All right, so when the switch is open, what is the ohm meter going to read? I just need to make sure, and there's a reason I'm doing this here, right? Because we need to get some basic understanding of some basic stuff. And this is this is my checkpoint with you. This is me checking your pulse when it comes to the electrical theory. All right, switch is open. What is the meter going to read? Please answer. Anybody? Somebody? Anybody? Yeah. All right, I got 1, 0. All right, the switch is open. What is the meter going to read? What is the resistance between these 2 points? I get this thing every year from everybody. All right. Let me ask you a question. When the switch is open, and let's say here, why not? Let's go crazy here, okay? Place component. Sources. Power sources. Let's get a DC power. Let's just DC or AC, doesn't matter. But let's have a DC, for example. Right? I'm going to place that battery here. And I'm going to change this one to an amp meter. Right? Now let's connect that. Boom. Let's put the resistor in the picture here. Boom. And boom. Now, I didn't introduce the ground. I wonder if this is going to let me, you know, what it's going to be. All right. I put that thing on. I turned it on. I'm going to take this off. So the simulation is on. There's 12 volts DC. Is there current flow in the circuit? Is there a current flow in the circuit right now at this point? Yep. Recordings on. I can see the message. I can see the chat. So it's not in the open. Okay, so Braden says, nope, there is no current flow. Okay, so if there is no current flow, is it because we are dealing with a high resistance or a low resistance? Come on. High resistance. How high is this resistance? Well, this resistance is extremely high because between this point and that point, we have, well, an air gap. So we're dealing with the resistance of the air. Now, the resistance of the air is not infinite. It does have some sort of a number, but for our purpose, the number is so high that we're going to consider that as infinite just to simplify things. So we have an infinite resistance between these 2 points. That means there is no current flow. Okay. Stop the simulation. And well, actually, let's see here. Start the simulation. The meter, the amp meter is showing 120.0 nano amps. Well, so that's probably some leakage of the, it's trying to be, exact. Yeah. But if you connect your multimeter, it's not going to react. It's going to show 0 amps. Okay. Nano amps, yeah, okay. That's considered pretty much 0 amps for our purpose here. Okay, stop the simulation. I'm just going to close that. Disconnect the whole thing. Put the components aside. Actually, let's connect this here. And let's turn this thing on to the ohm meter right now. All right. So when I close the switch, what is the ohm meter going to read? Yeah, give me some answers. When I close the switch, here, the switch is closed. When I press the simulation on, what reading am I going to get on the ohm meter? Ohm measures resistance, 330. Very good. You guys are smart. Let's check it, okay? Oh, wow, it's a miracle. We have a resistor of 330 ohms, and the ohm meter shows 330 ohms. Okay, all right, cool. All right. So let's just say I'm going to disconnect components here. Disconnect everything. Everything is out of the picture. If I press the simulation button right now, what is this ohm meter going to read? I'm waiting for some answers. Make sure you guys are awake. Infinite. Very good. Good. Okay. Let's just check. Oh, wow. Yeah, it just shows pretty much. That means it's infinite. Okay. All right. So now when I connect this switch, just like, let's make it a bit more visible here. Yeah. and I open the switch, what is the meter going to read? Can somebody answer that? Very high to infinite. Very good, Willow. All right. Okay. So what is the meter going to read when I close this switch? 0 ohms. Good, Gabe. All right. So we got the idea, right? Now, if you connect, well, let's just check. Here, infinite. Let's see, close the switch. Well, this one shows now. It shows because there's some wiring involved and maybe there's some leakage of current or whatever. It shows 100, pretty much 100 mega ohms, which for our purposes considered infinite. Close the switch. Boom, we get 0 ohms resistance. What happens if we connect the power supply in the circuit right here? Switch is open. Let's just put it here. And if we connect power supply here, what is going to happen if this, we change that to the amp meter here right now? What kind of current are we going to have? Okay, now it's no current because the switch is open. Close the switch. What kind of current are we going to have? You can go on voice. Well, DC current, yeah, but how high is it going to be? What will be the value of infinity, which means poof, right? Let's see what the meter is going to show, just for kicks. Start the simulation. Boom. Oh, this one's 109 kiloamps. Wow. This thing is really trying to be exact. Well, 109 thousandths of an amp with 12 volts. What power is that going to give us? That's going to give us huge power. Current times voltage, 110, let's say 100 kiloamps, 100,000 times 12. That's going to give us, those wires won't be able to, the fuse is going to pretty much be destroyed in the meter. That's a no-no. Right? Okay, so we got the concept, right? Good. Now, as far as our coaxial cable here, there we go. I'm just going to close this here. Coaxial cable, right here. Here is a piece of cable. Let's say we have a piece of cable that is, I don't know, about 10 inches long. Right? This inner conductor goes from one end to the other. The other end is going to look just like that, but on the other end. So this inner conductor just goes through the whole cable and it's not touching anything. Now here is the outer conductor. Does the same thing, goes through the whole length and it's not touching anything. And these two are separated by a dielectric, which means an insulator, and ideally it should be infinite number of ohms. It is not in reality because it does have some limitations, but let's say this is an infinite resistor. of infinite resistance. If you put an ohm meter between this and that, when you have 10 inches of cable, or 1 inch of cable, or 5 inches, doesn't matter, a short piece of cable, what is the resistance going to be that the ohm meter is going to read? Just a pure resistance. Here's the wire going all the way through, not touching anything. Here's the wire not touching anything. What is the resistance going to be? If you connect one lead here and one lead, the other lead over here, of the ohm meter, what is the resistance that the ohm meter going to show you? Aha. You see? Here's an ohm meter. What is this ohm meter going to read again with the open switch? Infinity. Okay. If you have these two not connected, and you connect one lead here and one lead here, what is the ohm meter going to show you? There we go. Infinity, right? Because those things are not connected. So another thing that I get from every year, all right, when I ask, all right, you connect one lead here, just a pure ohm meter from your multimeter. You connect these two and the meter doesn't react. What's the reading? And I'm not going to spend more time than we need to. And I hear the word nothing. Okay, please don't use the word nothing, because that's not a very scientific answer. All right, it's always something. It's either zero or infinite in this case, or any sort of resistance in between. Yeah? So just remember that. Now, when you connect one lead to this end right here, and you go all the way, all 8 inches to the other side, and you connect to that same wire, what is the meter, ohm meter, going to read? Connect one lead to here and to the other end of this inner connector on the other side, and the cable is about 8 inches long. What is your meter going to show? What is your ohm meter going to read? Very good. The resistance of the wire, which means, that's very good, which means that in our case, it's pretty much going to be a zero resistance. Yes, it is going to be very low resistance that does have some sort of a low number, but in order to simplify things, we're going to say that we are reading zero, all right? Which is going to be the same thing if we connect one lead to this outer conductor and we go to the other side of the outer conductor. It is also going to read 0 ohms because this here is connected to itself. It is itself. And on the other side is just a piece of copper. You connect that to that. The length is about 8 inches. You're going to have such a low resistance that we, for our purpose, can consider that thing to be a 0 resistance. Okay? All right. So that should help you with answering some of the questions here. There are other questions. We spent the whole hour last time in person talking about the characteristic impedance. Okay, it is important. And what is the characteristic impedance? The characteristic impedance is the impedance of the first, approximately the first meter of the wire. The impedance of the first meter, 1 meter of the wire. We use that characteristic impedance to determine what kind of impedance, output impedance of a transmitting equipment that we are connecting to this wire. For the purpose of maximum power transfer, the impedances should match. Okay? If the impedances are different, then not all the power is going to get through. Some of the signal is going to be bouncing back, feeding back to the transmitter, and it's going to make the transmitter heat up to the point that, plus you're not going to get the full strength of a transmission through this cable. Right. Now, I'm not going to tell you what it is because I'm going to ask you to look it up. So if there is a characteristic impedance question, what is the cable that we are using? The cable is RG6. Right. Here. Just firing up my board. There we go. We have a board. There we go. So RG6. Okay, RG stands for radio guide, and the 6 is just a cataloging number. The 6 doesn't mean anything. It's just something that can be registered as. Same as we have our social insurance number, for example. All right. Now, if you look at the cable next time you're in lab, and if you look at the print on the cable, you're going to see RG6, and you're going to see a letter U right beside it. Okay. What does that mean? Does anybody remember what that means? All right, not going to spend too much time. That U here, that means it's UV rated, ultraviolet, which means that this cable, if it's RG6U, it can be installed outside, exposed to the sun, and the sun is not going to damage that. So it does have a lifespan, but it's a very long one. Otherwise, if it's not UV rated, you can crush it with your hand very easily after about a year and a half of being exposed, maybe even earlier. Okay. All right, so that should give you some help or enough help with answering those questions that are on content. Okay. View as a student. Here, content, labs. Here's the work order, coaxial cable. See, there are those 5 questions. Right here. The group from yesterday, please copy those questions by hand, put them somewhere on the within the free space. copy the question and give the answer. Don't just give question 1, answer, question 2, answer. Just copy the whole question. It's not going to take you that much time. And give me the answer. 5 questions, 5 answers. It is in the rubric, and you're going to be evaluated on that. All right, cool. All right. Now, coaxial cable applications. RG59, RG6, that's the one that, for the most part, the internet provider will install if you have cable internet. RG11, it's a thicker cable, and RG58, those thicknesses pretty much are the same as far as the outside visual look at it, except they do have different impedances. Now, RG6, the one that we have used, it, well, mostly in the past was used for cable television, closed circuit television, CCTV. The CCTV was, well, TV cable distribution internally, like for internal distribution of the cable TV, like in the high schools. We have the broadcasting class, for example, in high schools. Remember when we were going back the years when you were in high school? And the broadcasting class would be broadcasting every Friday afternoon, some of their news and whatnot. It would be distributed by the closed circuit television system, and that coaxial cable was used. Later on, things went to towards the Ethernet type of transmission, so things are different a little bit now. All right, internet, broadband, we'll talk about that. For antennas, frequency limit, the bandwidth, 1000 megahertz or 1 gigahertz. Why did I put, why didn't I just put 1 gigahertz? It's because in the industry, when you're asking for the bandwidth, things are usually being answered in megahertz. So just pay attention to that, right? Now, characteristic impedance of RG6 is 75 ohms. Okay, all right. Now, RG59 is a little bit thinner. Network cabling, mostly in the past. Well, in the past. That now we use Ethernet. Before we used to use bus system constructed of coaxial cable. Video signal, mostly in the past. Some of the security cameras, also the CCTV, also is being called right now, as referred to as the security cameras as well, right? The older cameras used to use one power cable and one coaxial cable. And amateur radio, still in use, interchanged with RG59. Well, see, this one here has 1000 megahertz and this one has 1000 megahertz. So what gives, right? Same characteristic impedance. There is something that gives, okay? Now here, the differences between RG59 and RG58. Here, mostly using amateur radio antennas. So here, these two, well, that depends what kind of a transmitter you have, what kind of a system. Do you have a transmitter with the output impedance of 50 ohms or 75 ohms? And that's the cable you use to match the impedance. There's a big difference between 50 and 75 ohms when it comes to radio signal transmissions. If you use wrong cable for the transmitter that has different impedance, you are going to deal with a lot of heat loss and signal loss. You're not going to have power that you want. RG11, well, here it's a thicker cable, and the bandwidth is 3000 megahertz, 3 gigahertz. It's the impedance is characteristic impedance 75 ohms. Want to know more? Click here. I got that from one of those movies. I think it's like something about killing bugs or something on a different planet. Yeah. All right. Attenuation. See here's where the difference is between RG59 and RG6. See that? Attenuation. What's attenuation? Attenuation is signal degradation or signal becoming weak based on, well, whatever. Based on resistance, based on impedance, based on capacitance, inductance, or therefore reactances, and length, which has to do with how. So, same thing here. If I shout, if I scream something, right? The person who is standing 10 feet away from me is going to hear me very clearly. About the person who is standing 500 yards away from me is not going to hear me, even if I scream. It's not going to hear me as the first person, as well as the first person, because my voice, as it travels through the air, the power of my voice is going to attenuate, right? Become weaker. Right? Now here is frequency in megahertz. Cable RG59, RG6, and contestant number 3, RG11. Let's see what happens. Now, frequency 5 megahertz, 55 to we kind of go up with the frequency here. Here's the low frequency, here's a high frequency. Let's see what the attenuation is per 100 feet. And just for kicks, we did the per 100 meters, decibels. Decibels. Now, decibel is a referential scale. Okay. All we need to know for this book, I'm not going to give you a lecture on the logarithmic scale and decibels and whatnot, which is just not part of the curriculum of this course. However, what we need to know is, as a referential scale, power. If you raise power, if you double the power, okay. So you have whatever, the light bulb that consumes 100 watts, or a loudspeaker that puts out 100 watts of volume of sound, or whatnot, okay, something, whatever power, okay. If we have a speaker that is pumping out music with the power of 100 watts, you double the power, which would be 200 watts, you have raised the power by 3 decibels. Okay, so from, let's say from 10 watts, raise it 3 dB, you get 20. Raise it 3 dB, you got 40. Raise it 3 dB, you got 80, and so on. It goes down as well. Right, so if you have 100 watts, lower it by 3 decibels, you get 50 watts. That's how it works. The magic number is 3 when it comes to power. When it comes to voltage, in some of the cases you're going to have to display the voltage on the oscilloscope. And if somebody asks you to raise the voltage by, well, double the voltage, for example, with the voltage, the magic number is 6. Right? So you double the voltage, you have raised it 6 dB. Power is 3. Double the power, 3 dB. Okay, so now we have some idea of what these numbers would mean. Okay, all right. So signal attenuation, and here are some conditions. Room temperature. Okay, at 5 megahertz, RG59 is going to attenuate 0.89 decibels per 100 feet. I'm just going to use the feet here. You can look at the meters if you want, you know. Now, RG6, even though they have the same bandwidth and same characteristic impedance, so looks like there is no difference. There is difference between these two cables, the attenuation. RG6 is going to attenuate less, so the signal is going to, you can transmit the signal further in RG6. You can transmit the signal even further in RG11. Okay. Now, so you can tell that the RG11 cable is going to be able to transmit the signal over longer distance than RG59. And RG6 is the mediocre thing. Why don't we just have RG11 and forget the other two? Well, price is one thing. Price of the cable, the amount of copper that's being used, the amount of the tool, the price for the tools, connectors, and whatnot, the whole overall installation. So sometimes if you don't need a longer distance, then you just get the cheaper cable because it's enough. You don't need to get a more expensive one. Now also, as the frequency goes up, see 5 megahertz, 55, and so on. So here's a low frequency, here's a high frequency, okay? The attenuation is also different per frequency. RG59 is going to attenuate the higher frequencies more because the higher frequencies do not have enough meat on the bones. They don't have enough of the power, of the oomph to push their elbows through, to push the weight through. So low frequency, it's a rumble, the bass, boom, it just goes like a steamroller. It has enough energy to travel further. Now, the higher frequencies do not have as much energy as the lower frequencies, so they are going to become weaker quicker. So the attenuation in the cable goes by the cable type, and also it depends on the frequency. Higher frequencies are going to be attenuated or weakened more, destroyed quicker than the low frequencies. We're going to skip this slide because that's just for you to know, nice to know. That has something to do with the cable, the cable TV channel frequencies. Very high frequency VHF, channel 2 cable TV up to channel 13. That's the VHF band. All right. General television frequencies, well, very high frequency, low band, mid band, high, and so on. You can just take a look at this thing. This thing pretty much becomes a history right now. Now, here's something that's called an RF amplifier. Very simple thing. It has an input and it has an output. These are the two main things. You insert the signal here with a certain strength. Let's say cable TV signal. And you need to boost it up to send it further. Why? Because maybe you need to connect one. Where's my board? There it is. Let's say you need to connect. Here's the amplifier, okay? And you need to connect one long RG11 cable with taps along the way, taps along the way, taps along the way, and so on. And from there, you're going to split that into the TV. All right, and you're going to split that onto another TV. You're going to split that somewhere onto another TV, and so on. That's CCTV. So here is from the city, provided from the city, and then that's the internal inside. Here's the amplifier that transmits the signal. So you need to boost enough so you have enough signal here to distribute with all those TVs, for example. So here is the volume control, gain. And there's that mystery control that says tilt. Ooh, all right. Before we get to that, those two controls, well, this one is pretty much obvious, self-explanatory, how much you want to amplify the signal. It's an RF amplifier, radio frequency amplifier, or sometimes called distribution amplifier. All right. Now look here, there's another connection here and there's another connection here. The signal comes in quite strong from the city. If you want to plug in a test television set into it, it will be too strong for that TV to handle. So here is the test or the input test, but this is actually an output. It has the input test signal, so you can see what's on the input. And it's lowered by 20 decibels, so the TV can handle that signal. And over here on the output, same thing. We have like a test output or output test output. Here's an input test output. Here's an output test output. Lowered by 20 dB, so you can check what's on the output. Let's get to this thing here. Go back. See this thing here? Let's say we're dealing with the RG11 and we're transmitting cable TV signal. Lower frequencies travel far. Higher frequencies, they are not doing so well over the greater distance. The longer the distance of the cable, the lower frequencies have a harder and harder time punching through and traveling. Okay. So at the end of the cable, at the end of the run, you might find that the lower channels of the cable TV transmission are going to appear just fine. But the high channels that are utilizing higher frequency carriers are going to be snowy and the signal is going to look not as good. Because that will be the characteristic. We're almost done for today. Where's my pencil? Yeah. Here is something that's called a slope. Here's the length. And here is the, let's say, well, dB signal strength. The longer the cable, the weaker the signal. Sorry, this will be the frequencies. Yeah, frequencies based on length. But these are the frequencies. The higher the frequency, the weaker the signal. So why not at the input of the right at the amplification station, reverse that. Here are the frequencies. Here are the dBs. Well, we can do the same thing. We can amplify the higher frequencies more right off the bat than the lower frequencies right here at this amplifier by doing the tilt, or sometimes it's called a slope, depending on who makes it. So when you go to the far end of the cable, you're going to get more or less a flat line. Right? Because when you amplify the high frequencies more at the beginning, as they travel along, they're going to become weaker. So that thing is going to equalize itself. Yeah. So that's the idea of the radio frequency amplifier and a slope. Now, next time we see each other, it's probably going to be tomorrow, on Thursday. I'm going to finish this up. I'm going to publish that, and after tomorrow, I'm going to open up the test. All right. So now, here, before we finish, Make myself look like myself. Content, nope. Evaluations, right? And submissions. Here, coaxial cable, I can make that visible right now. All right, it's going to appear right now because I gave you that information on that will be able to you'll be able to answer the questions. Cool. So that's pretty much it for today, and I'll see you tomorrow. Thank you, and well, enjoy the rest of the day.